The authors acknowledge that this podcast was recorded on the traditional, unceded lands of the Lekwungen peoples. Good morning, and welcome back to Stories from Space. I'm your host, Matt Williams, and today we're going to get into our final installment in the Great Migration series, how human beings may someday come to settle the entire solar system, by taking a look at Neptune and the Trans-Neptunian region, which includes the Kuiper Belt and the Oort cloud, and of course all the many planets, or dwarf planets if you're someone who embraces the current IAU definition, that exist in these regions. That includes Pluto, its largest moon Charon, as well as Eris, Haumea, Makemake, Sedna, Gong, Quaoar, Orcus, and the many, many more larger objects that have been discovered in the past few decades. And as we covered in previous episodes, settling on any of the bodies that are beyond Earth, be they planets, moons, large asteroids, it represents a major challenge. But with the right strategies, the right know-how, the right kind of commitment, and of course the requisite technology, it can be done. And the benefits would be quite substantial. And of course, it's also important to take into account that by the time humanity has the option of settling around Neptune and the Trans-Neptunian region, many of those technologies will already exist and be in widespread use. So there's not going to be a huge learning curve involved by the time that settling on moons like Triton, on Pluto and Charon, and the aforementioned dwarf planets will become possible. And the same goes for the strategies and the means through which we make life in this region of the solar system livable. In fact, the methods used for settling within the asteroid belt, within the Jovian system, the Cronian system, that is Jupiter and Saturn respectively, and the Uranian system, they will already have been tested and validated, and so with some minor modifications, they could be adapted to the Trans-Neptunian region without much difficulty. Nevertheless, it would still represent a huge undertaking. So, when it comes to the outer solar system, Neptune and beyond is one of the least explored and understood regions. So, our knowledge of the region would have to increase dramatically in order for us to ever really consider establishing settlements there. But, again, assuming we have already established settlements all the way up to Uranus, Neptune and the Trans-Neptunian region would be a relatively easy hop, skip, and a jump. In terms of what we do know, Neptune, like Uranus, is predominantly composed of hydrogen and helium, but also contains more volatile elements compared to your other gas giants, such as water, ammonia, methane, and various hydrocarbons. And it is the presence of methane that actually gives both Uranus and Neptune their characteristic color. And also like Uranus, because many of the elements, the volatiles that it contains, are under such pressure and density, they become solid as one descends through the atmosphere. So, Neptune, like Uranus, is known as an ice giant, to differentiate them from Jupiter and Saturn. And lastly, like Uranus, Neptune is believed to experience diamond rain within its atmosphere. As a result of carbon under intense pressure, it solidifies to form diamonds, which then fall deeper into the atmosphere in the form of precipitation. As to what separates Neptune and Uranus, Neptune has higher concentrations of methane in its atmosphere, and this higher concentration of methane is why Neptune has a slightly bluer hue than Uranus. Another unique attribute that Neptune has is its name. Unlike the other solar planets, it is the only one to be named after a god in the Greek pantheon rather than their Roman equivalent. In this case, Neptune was the god of the sea, and its intense blue color had a lot to do with the inspiration for that name. Lastly, Neptune is unique among the gas and ice giants in that it has one particularly large satellite, Triton, which was the only satellite found around Neptune that is large enough to achieve hydrostatic equilibrium, which is to say that it has enough matter and density that it collapsed under its own gravity to form a spherical shape. And like its parent planet, it was not discovered until the mid-19th century by English astronomer William Lassell. So unlike the other gas and ice giants, Triton accounts for a significantly large portion of the mass fraction of all the satellites that surround Neptune, 99.5% of it. And based on this, scientists believe that in fact, Triton did not form around Neptune, and what we see there are not its original system of satellites. And so scientists believe that Triton is actually a minor planet that formed in the Kuiper Belt, much like Pluto, Eris, Sedna, Haumea, Makemake, etc., and was kicked out by gravitational perturbances and fell into orbit around Neptune and caused a very, very serious tidal disruption that led its other moons to collide and break apart, and for that debris to eventually settle into the smaller satellites we see now. Whereas Triton, as we see it today, is the result of a lot of that debris coalescing with the original captured minor planet. And like many moons in the outer solar system, scientists believe that its structure is differentiated between a surface composed of ice, in this case, nitrogen ice, as well as water ice. Then these two make up the crust. And beneath that, it is believed that a liquid water ocean exists. And this is made evident by the cryovolcanism that the Voyager 2 probe noticed as it made its historic flyby in 1989. And this was the only mission that's ever conducted a close flyby with Triton. Nevertheless, what it revealed was very interesting. In addition to the cryovolcanism, where liquid nitrogen and water were erupting through the surface, it also noted a tenuous nitrogen atmosphere. And like other ocean worlds, scientists believe that the core is composed of a silicate rock outer core and an iron-nickel inner core. So based on what we know about Io and Europa, Enceladus and Titan, and the other ocean worlds of the system, the presence of this interior ocean and the cryovolcanism on the surface, this is believed to be the result of tidal flexing in the interior caused by the gravitational interactions between Triton itself and Neptune. And so, like other ocean worlds, it is believed that this interior ocean that Triton has may be capable of supporting life. And this is bolstered by other evidence which showed black material being ejected by its surface plumes, which were believed to be organic molecules. Moving now to Pluto and its largest satellite, Charon. This is another planet in the outer solar system that for the longest time was the least understood. And like Neptune and Uranus, it's been visited by only one mission, and that is the New Horizons mission, which flew past in the summer 2015. And the images it acquired were the sharpest ever taken of the planet and finally gave astronomers a much better understanding of its surface features, of the geological activity and the climate and its atmosphere, and really everything going on the surface that makes this body such a very interesting and dynamic place. And speaking of its atmosphere, this is composed largely of methane that has sublimated from exposure to the sun, and this is due to the composition of Neptune, which consists of frozen nitrogen, frozen methane, and frozen carbon monoxide. So just about all the volatiles with the lowest melting points, and therefore also the lowest freezing points, at this distance from the sun, they all form ice that is condensed and solidified to the point where it's like granite. It's like standing on a rocky planet. And similar to what we see with a lot of the icy moons around the other gas giants, it's the dynamics of this ice, the way it behaves a lot like tectonic plates or like volcanic activity. Except, of course, in this case, we're talking about cryovolcanism. So volatiles under pressure breaking through the surface in the form of water and then instantly sublimating to form a bit of an atmosphere. Now, Charon is also a very interesting customer because it is roughly half the size and 1/8 the mass of Pluto. So scientists often consider Charon to be co-orbiting with Jupiter rather than orbiting around it. And because of the way they closely orbit each other, the two bodies are tidally locked with each other, so one side is constantly facing towards the other. So if you're standing on the surface of Pluto, you would look up and constantly see one side of Charon, in the same way that Earthlings look up to the moon, which is also tidally locked with our planet. So if you could stand on the surface of Pluto or Charon, look up into the sky, you would see the same face of the other body looking back at you all the time, in the same way that we see only one side of the moon at night. And like Pluto, it's predominantly composed of nitrogen and methane and other frozen volatiles. And this body may also experience cryovolcanism, which is made evident by the presence of organic molecules that are on its surface that, when exposed to the sun, become reddish-brown. And this is very common throughout the outer solar system, and it's known as tholins. And these may have been caused by cryovolcanism, which caused them to erupt onto the surface, or it's possible that they were transferred from Pluto's tenuous atmosphere, because in fact the two bodies are close enough that this could take place. And whereas Neptune wasn't discovered until the mid-19th century, Pluto was not discovered until 1930, and Charon not until 1978. The credit for which goes to Clyde Tombaugh and James Christie, respectively. And what's also very fascinating is much of the evidence that was returned by the New Horizons mission indicated that, in fact, Pluto and Charon could also be ocean worlds, that there could be liquid water oceans maintained either through tidal heating or through the decay of radioactive elements in the core, or both, that allow for the existence of liquid water in the interior, with estimates indicating that it could be 100 to 180 kilometers deep. Now, beyond this, you have the aforementioned dwarf planets, most of which orbit beyond Pluto, with the exception of Orcus, which actually has a slightly tighter orbital radius around our Sun. But beyond Pluto, you have, in order, Salacia, Haumea, Rheor, Makemake, Gong, Eris, and Sedna. Like Pluto, these planets all have very, very long orbital periods, taking hundreds, or in the case of Sedna, 11,400 years to complete a single orbit of the Sun. And of these, only one, Eris, is comparable in size, but also greater in mass and density than Pluto. This was part of the reason for the Great Planet Debate. If in fact astronomers were finding satellites beyond the orbit of Pluto that were comparable in size, then what did they call them? Because by and large, all the other dwarf planets are about a third or two-thirds, at most, the size of Pluto and significantly less in terms of mass. Nevertheless, within this population, as well as Pluto and Charon, and around Neptune itself, the possibilities for exploration, research, and even living are really quite significant. Now, in terms of what this would look like, well, very similar to what we explored in previous episodes dealing with the other gas and ice giants, settlements in these regions would most likely consist of space stations that would orbit around the largest body and would allow for access to these bodies and their satellites. And these would likely take the form of pinwheel stations or O'Neill cylinders, essentially structures in space that rotate to simulate Earth-like gravity. And this is the greatest barrier to long-term living in the outer solar system, which is to say the low gravity. So, for example, on Triton and Pluto, the gravity is less than 1% that of Earth's. And on Charon, it gets even lower, less than 0.3%. And this is close to what astronauts experience in microgravity. Whether they're aboard the ISS or traveling to deep space, the risk of long-term exposure is the loss of muscle mass, bone density, organ function, eyesight, and even psychological, neurological, genetic changes over time. So while settlements on the surface would not be feasible, short-term visits certainly would be. People would be able to visit the surface of these bodies, possibly for the sake of resource extraction or tourism, and spend the rest of their time aboard a space station where the comfortable 1G of gravity ensures that their health is maintained. And this low gravity, though, has an upside, which is a very low escape velocity. It takes a small fraction of the energy to achieve escape velocity compared to what you would need to generate to send payloads to space from Earth or just about any other body in the solar system. And of course, these habitats would have to take into account radiation shielding as well, because in addition to the microgravity-like conditions, Galactic cosmic rays are a serious problem in the outer solar system. But with sufficient shielding, habitats in this region of space could be entirely livable and populations able to thrive. And so resources could be mined and extracted on these bodies and also manufactured. The low gravity would facilitate certain types of manufacturing processes, and they could be launched into space using very little propellant. Or, in keeping with the tradition of the outer solar system hurling comets and asteroids to the inner solar system, and at one time minor planets like Triton, these payloads could be hurled into space using kinetic launching systems or magnetic launching systems. A slingotron is a concept that relies on these very principles. And so, with proper precision and guidance, of course, payloads of methane, nitrogen, and other volatiles that were still in their icy form could be hurled into the inner solar system, where they could be used especially for terraforming purposes. Mars and Venus, for example, both require significant amounts of nitrogen, ammonia, methane, and also hydrogen, depending on which planet we're talking about here. The necessary greenhouse gases or chemical reactants could be sourced from the outer solar system and provide for the interior. In addition, Neptune, much like Uranus and the gas giants, it has a considerable amount of hydrogen and helium in its atmosphere, which could be scooped up and used to power fusion reactors and fusion engines and everything of the sort. To quote Robert Zubrin, the outer solar system could one day become the Persian Gulf of the solar system, providing the fuel that would meet our transportation and energy needs, as well as other vital resources, which of course include metals and silicate minerals. But by and large, the resources of the outer solar system consist of volatile elements in ice form, and then of course includes water, which in terms of resources is absolutely essential to living. And so the outer solar system could also become the wellspring of our future civilization. And ice miners, much like what is depicted in the series The Expanse, could become a reality far beyond the main asteroid belt. Which brings us to the Kuiper belt itself, which, much like the main asteroid belt, is a massive ring of smaller bodies with some larger bodies, all the dwarf planets that were previously mentioned, that orbits the Sun. But whereas asteroids in the main belt are predominantly composed of silicate minerals and carbonaceous compounds and metals, the Kuiper belt consists of ice-steroids, which is to say they're composed of ices in the form of methane, ammonia, and water. In addition, the Kuiper belt is 20 times as wide as the asteroid belt, and as for its overall mass, estimates say that it could have 20 to 200 times the overall mass of the asteroid belt. So a lot of material there to work with. And while it would be irresponsible to ever advise that humanity should comb these belts and use everything there for the sake of resources, nevertheless, committing to extracting a portion of these bodies and using them for their materials, while leaving others as designated conservation areas, would be in keeping with sustainable practices. And that still leaves an unfathomably large amount of material to use. And much the same is true for bodies like Pluto and Triton and others that are believed to be ocean worlds and have interior oceans. Whether or not you want to try and access that water is a very debatable, very ethically complicated topic. Because if in fact these bodies are capable of supporting life, then we would want to do the absolute minimum to disturb any life there. But even with a strong conservationist approach in place, that would still leave a huge amount of water and other volatile elements that would be accessible. So, as I said, even though there are sources of silicate minerals and metals in the outer solar system, these would best be used, in my humble opinion, to manufacture the bases and rotating stations on site, a case of in situ resource utilization on a very grand scale, while the primary resources would consist of water, terraforming gases, and, of course, lots of hydrogen and helium. And this, of course, addresses another major challenge of settling in the outer solar system, conducting tourism there or business there, which is the extreme distances involved. For starters, Neptune is almost twice the distance, which is to say roughly 4.5 billion kilometers from the Sun, Uranus being 2.8 billion kilometers. Now, considering that it would take, using conventional propulsion, 6 to 9 months to reach Mars, one of the closest planets to Earth, a one-way trip to Neptune would take decades. So commercially, it's really not feasible, especially if you want to go to the Trans-Neptunian region, where the distance just keeps multiplying, and considering that you want to return as well, factoring in the return trips and all the time spent reconnoitering or conducting resource extraction, you're dealing in timescales that are completely unrealistic for human standards and human development. So, of course, more advanced propulsion systems would be necessary. And this is where having local sources of helium and hydrogen comes in really handy, because at this point we would be talking about propulsion systems more advanced than your nuclear thermal or nuclear electric engines. We're talking fusion engines at this point. But as noted earlier, at this point in the game, if we are contemplating settling the outermost parts of the solar system, then chances are we've already settled everything up to that point, and all of these technologies were developed during that time in order to facilitate that very process. So once again, it comes down to if you have the requisite technology, energy, and resources at your disposal, you could be capable of mounting missions to the outer solar system, of setting up shop there, creating in situ resource utilization facilities that would provide fuel and building materials so that permanent habitats could be created there. And then over time, this would facilitate the emergence of an export economy, based mainly around volatiles and also fuel, which would provide for the more densely populated areas of the solar system at this time. And so in terms of the overall benefits, well, as with other major settlement efforts, there's, of course, the resource potential. Having access to the outer solar system's resources and planets would help maintain the momentum established by settling neighboring planets and within the main asteroid belt and around Jupiter and Saturn, which is to say the era of post-scarcity economics. With so much in the way of resources available to us, the very basis of wealth would disappear. Without scarcity, there would be no such thing as the impoverished and the wealthy, and this in turn would have significant social and political implications. And of course, the ability to settle into the outer solar system, having new places to explore and live and work, would also lead to new social developments that'd be very, very interesting to see. And there would also be the potential for scientific research. At the edge of the solar system, we could conduct all manner of astronomy, and we'd be doing so with very little interference from other planets and bodies in the solar system, not the least of which would be the search for extraterrestrial intelligence. Placed out in the Kuiper Belt, or beyond even, we would be capable of listening for extraterrestrial transmissions like never before. And in addition, there is some theories that an extraterrestrial intelligence may have already visited our solar system in the form of probes. They would send their technology on ahead to scout, and that perhaps we would be able to find derelicts or even functioning probes still there. Among certain contact optimists, as they're typically referred to, it is conjectured that, yes, in fact, searching the asteroid belt and the Kuiper Belt would be the best bet for finding examples of self-replicating probes or interstellar probes that have come about conveying messages or were just doing recon. So the opportunity to resolve the Fermi paradox is there as well. And of course, there is the immense potential for conducting astrobiology studies. Looking at Neptune's moon Triton and the Trans-Neptunian region, all the ocean worlds that are there, it presents us with an opportunity to see if life did in fact emerge in the outer solar system and what forms it might take. Because, of course, looking at the potential for life within the Jovian moons and the Cronian moons around Jupiter and Saturn, it is likely that should life exist there, it will take on a certain forms and characteristics. But out beyond the point where all volatiles, including nitrogen and methane, freeze solid, it's possible that the chemistry will be different, that a different type of life will have emerged there. So while this is not something that we could be contemplating today beyond speculation and theory and some really good science fiction, it is something that we may be contemplating someday. And there's a long road to hoe before we get to that point, but that point may someday arrive. So this is our final installment in the Great Migration and how human beings may someday settle the entire solar system. In the not too distant future, I would like to get into the next logical extension of that and look at how human beings may someday travel to other star systems and what the potential for finding life might be there and what potential there could be for establishing new outposts of human civilization there. My personal thanks to everyone who has listened to this series in its entirety. I hope it's been enlightening, informative, and at the very least, a little entertaining. And so I say to you and all my other listeners, thank you for listening. I'm Matt Williams, and this has been Stories from Space.